Yeah, that's
recording now. Right, I'll just sum up that again. So we're doing step input into RC to find an expression for the voltage across the capacitor at time t. We're going to use Laplace transforms. So the circuit, 20 ohm resistor in series with a 5 farad capacitor. And by Kirchhoff's law, this 10 volt step input would be shared between these two components at any one time, such that these two voltages add up to that 10 volts. So using the voltage divider rule that we learned earlier on the course, we can say that in the time domain, the voltage across the capacitor is equal to the applied voltage times the impedance of the capacitor over the impedance of the resistor plus the impedance of the capacitor. Yeah?
Mm-hmm.
Okay. So what we then do is we write, like we did before, we write expressions for these quantities in the S domain. So we could say ZC S is equal to 1 over CS. Yeah. From your table. So that's 1 over 5S. R in the S space is just equal to 20. Yeah. And the voltage applied in S space is equal to 10 over S. You're all happy with where those come from?
Yeah.
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 Right, I'm going to have to go on another page now. So let's just save that one. Add another page. So
what was that? You got ZCR, and then what was the other one?
I'm just going to write them out here again, all right? Because we've got
okay.
RS.
VS equals 10 over S, mate.
Was a 20.
Right.
Yeah. ZC is equal to 1 over 5S. Yeah. And VS, the supply voltage, is equal to 10 over S.
Mm-hmm.
Yeah.
Yeah.
So we can say the total impedance of this circuit in ZTS is equal to R plus 1 over CS. That is 20 plus 1 over 5S. So that's an expression for the total impedance of that circuit in S space. You all follow that?
Yeah.
Yeah?
Mm-hmm.
Mm-hmm.
And then you need to use the voltage divider rule we had earlier. So we can say that V C in S space is equal to, that was equal to the supply voltage 10 over S times I'm just looking back now. ZC. So ZC is 1 over 5S. And then it's ZR, so it's 20 plus 1 over 5S. Do you all see where that comes from? Just going to make that a little bit neater.
So S take away, is that, Mike?
Plus.
Oh, it's plus.
No, it's times.
Oh, right, okay.
Oh, that. Oh, yeah. I thought you meant the 20
Yeah.
plus 5 over S.
No.
1 over 5S.
What is S?
That's
S space,
just
mate.
as designating that we're in the S
S
domain. So that's a bit annoying that you were missing last week, Dan. Or the last time I taught, I should say. But Laplace transforms is about writing an expression to have taken a problem in the time domain that you'd normally solve using integration.
Yeah.
We put it into a new domain called the S domain or S space. Yeah.
Yeah.
So we've converted our resistor to S space, and all you do is just the number. So we got a 20 ohm resistor. So R in S space is 20. Notice that you drop the units off. You don't call it 20 ohms anymore. It's just 20.
Yeah.
The capacitor in S space is 1 over C times S.
Yeah.
So we've done 1 over 5S. Yeah. And then and the voltage in S space is the voltage value over S.
Yeah.
You got the table of Laplace transforms from previous weeks.
Me?
Yeah.
No. No.
You should have that handout, Dan. It's in the book.
What, from last time we did lessons?
Yeah, we got a
I got series harmonic resonance.
See.
Yeah, because I missed that lesson, so I probably need that book. So
right, just
if you email it to me, I can print it off when I'm next at work.
Yeah, well, you kind of really need it now to know what's going on.
Have you not got
Can
it?
you send me a picture of it, Kieran?
Yeah.
I'm going to see if I can. Yeah, can you do that, Kieran?
Yeah, so I'll do that now.
You can
I'll
put a
get it up
file
on
in
the
the
phone.
chat or something.
Where are we? Well, you should have it, Dan.
Yeah, I've got it now. Cheers. I'll keep it up on my phone. Who's that?
That's peas and pie.
Right. Are we ready? Are we ready to continue?
Yeah.
Yeah. Right. So what we've got to deal with now is this fraction here that I'm ringing around with this pointer. Yeah. And we could write that denominator as being over 1. And therefore, we've got a fraction divided by a fraction. And we deal with that by turning the denominator fraction upside down and multiplying. So what that means is we can write VC in S space is equal to 10 over S, so we leave that as it is, times 1 over 5S times 1 over 20 plus 1 over 5S. Yep. All follow that?
Yeah.
Yeah. And then what we can do is keep this 10 over S here and see why I'm doing that in a minute. And then we multiply out the other two fractions. So on the top we got 1 times 1 is 1. And on the bottom, we're going to put 5S times 20 plus 1 over 5S, like so. Yep.
Mhm.
All right.
Yeah.
And then lastly, we can multiply out the last part to get, I'm running out of room here. Just let me redo that a little bit further up. I need to learn to conserve space a little bit more on this. 10 over s times 1 over 5s brackets 20 plus 1 over 5s. All happy with that? And then we can multiply out again. So we have 10 over, right, and what would you have? And multiply all of this by s. So we'd have no, I can see what I've done here. 1 minute. We multiply out these brackets. So equals 10 over s times 1 over 5s times 20 is 100s. And then we get plus 5s over 5s. So what does that leave?
1s. Or s.
Nope. 5s divided by 5s.
1 and
1. Yeah. Yeah. All right.
Mm-hmm.
All of you, yeah?
Yeah.
Right. New page. So we then what we were left with on the previous page was 10 divided by s times 1 over 100s plus 1. Yeah. Multiplying that out, we get equals 10 divided by s times 100s plus 1. All right.
Yeah.
Yep.
Have you all followed that reasonably
Yeah.
well? Yeah. What we can do, what we need to do now is this is where we need to say using partial fractions. Remember them?
Nope. Oh yeah, yes. I don't know how to do it.
No, well, we're now going to reintroduce you to that, Peter. What we can do with partial fractions is say that this expression 10 divided by s 100 plus 1 is equivalent to, and then we write I over s plus b over 100. That's 100s plus 1. Yeah. Write it as two partial fractions. Yeah. All follow that?
Yeah.
Mm-hmm.
Yeah.
Then we need to find our common denominator. So a common denominator for these two fractions here is what we had in the first place, s 100s plus 1. Yeah. So to get the fraction with a on top, 2s times 100s plus 1, we had to multiply by 100s plus 1. So what we do at the bottom, we've got to do it to the top. So we end up with a 100s plus 1 there. And then over this side, we'd need to multiply this 100s plus 1 by s to get the common denominator. Do you see that? So that's going to be beta. Here is going to be, sorry, plus b times s. Yes or no, all of you?
Yeah.
Yeah.
I think I get it, yeah.
All right. Anyone remember what you can now do?
Can you eliminate? Oh no.
It's called equate numerators. Because the denominators are equal, over here we got s times 100 s plus 1, and over here we've got s times 100 s plus 1. Yeah, because they're equal to each other, then the numerators must also be equal. So 10 must equal a times 100s plus 1 plus bs. Yeah, so we can say 10 is equal to I 100s plus 1, close brackets, plus bs. Yeah, that's called equating the numerators. Again, just save that page. So, well, our equated numerators were 10 is equal to I 100s plus 1 plus bs. What we now do is let s equal a number that will allow one of these terms to cancel. Yeah, to be 0. So if we say that s equals 0, then that becomes 10 is equal to a times 100 times 0 is 0 plus 1 is 1. So a times 1 is equal to b times 0 is 0. Yeah. So therefore I equals 1. All happy with that?
Yeah.
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 Now, what we have to do then is let 100s plus 1 equals 0. Yeah.
Yeah.
Then we need to rearrange that. So we'd have 100s equals minus 1. Move the 1 across the other side. S is equal to minus 1 over 100s. Follow that?
I think so.
Yeah.
Which is in probably a simpler form is equal to minus 0.01 minus 100th. Yeah. If we then plug that in, so we say therefore 10, in this case, the A term is going to cancel out. Yeah. Because we've said we made 100s plus 1 equal to 0 and rearranged it to find s. So the value of s that will make this term 100s plus 1 equals 0 is when s is minus 0.01. So we then plug that into our equated numerator. 10 is equal to 0 plus b times minus 0.01. Yeah. Which is 10 is equal to minus 0.01b. b is equal to 10 over. Yeah. And that is equal to minus 1,000. All follow that?
Yeah.
All right.
Yep.
Therefore, we can plug that back in. Just save the page. Just plug that back into our partial fractions. So what we can do, then we can plug the A and B values in now. So we can say that 10 over S running out of time. Should just get this done, I think. 100 plus 1 is equivalent to, and the value for A was, I thought we got 1. Value for A. No, A is 10. A is 10.
No, we got A equals 1.
Yeah.
Let me go back at that then, Peter, because that's...
Should be 10, shouldn't it? Because 10 equals A times 1 plus 0.
10 equals A brackets 1 plus 0. We got 1.
Yeah, it should be 10. And now try to find it.
That's when you done the equate numerators.
Yeah, here. 10 is equal to
Yeah.
A times 1. So A is not equal to 1, it's equal to 10. See that, Peter?
Yeah.
Slip with a pencil. So we can say that 10 over S plus 1 is equal to A, which is 10, over S. And then B is minus, so we put the minus in there, 1,000, over 100S plus 1. Yeah? What we now need to do is we're going to leave this alone, but we're going to simplify this bit so that S is on its own. So what do I need to do to get S on its own here? I need to divide through by
100.
Yeah. So 1,000 divided by 100 is 10. Yeah. Over S plus 0.01. Yeah. Now, you should notice that this looks like something in the table of Laplace transforms. A over S. And this looks like something in the table of Laplace transforms that look like A over S plus B. Yeah. So therefore,
Exponential decay.
that bit's exponential decay. The right-hand side, a over s plus b. Left-hand side is a constant. Yeah. So we can transform back. And say VC at time t is equal to, and this 10 over s bit here is equal to 10, isn't it? When you transform back, constant 10. Follow me or not?
Yeah.
Yeah.
This one and this one is 10 times e to the minus 0.01 t. That's our expression, and where you're most used to it is that we've got a common term here with these two 10s, so we can take that outside of brackets and put inside the brackets 1 minus e to the minus 0.01 t. Close brackets. That's your exponential rise to a limit.
Right.
So 10 is your limit. Remember what I said? We're expecting 10 volts. We're expecting exponential rise to a limit, which is 10 volts. Remember when we done sines, this minus 0.01 here is the time constant. Do you remember that?
Yeah.
Yeah. Okay.
Yep.
So if you're asked to do an expression for the capacitor voltage at time t, then you're going to be into partial fractions, all right? And you'll see they'll also come into find an expression for a current in another type of circuit, which we're going to look at next, all right? So room time's coming to an end. So I'm going to end this one and start another one up straight away, all right?
Yeah, okay.
Yes.
Righto.